All right, guys, welcome to lesson 4.7. We're going to be talking about something known as a position function and a velocity function today. We're going to find out how they're related to each other and then use them to find some stuff about a moving object, like where the object's located, where the object's distance has been traveled, and what's the velocity and speed and direction, all that good stuff. So let's go ahead and jump in and see what's up with this stuff. All right, so let's take a look at our first thing here. What is a position function? A position function is a function that indicates the position of a moving object as a function of time. Often we use these letters here, f of t equals s. T represents the time, and s represents the coordinates of the object's position. Okay, so for example, if I told you we have f of 2 equals 5, what that could mean is that could possibly mean, for example, at t equals 2 seconds, the object is at coordinate 5. So if I were to give you guys like a number line, for instance, say an object, let's just say the object starts here at 0. After 2 seconds have gone by, the object's over here at position 5. So after 2 seconds, it's now there. That's what that means. So basically, the input is how long it takes. The output represents where it's located. Okay? And that's what we call a position function. So how can you tell how much an object's position has changed over time? Well, you would find, if you want to find out how much the object's position has changed from time 1 to time 2, what you do is you would find the position of the object at time 2, you'd find the position of the object at time 1, and you would subtract them, right? That will tell you how far apart it is. And so using S to represent position at T2 and S1 to represent the position at T1, the change in position is S2 minus S1, which you could also just think of that as F of T2 minus F of T1, right? And we represent that with a little triangle in front of the S, and that triangle is called delta S, just so you know. And what that delta means is it means how much the object's position has changed over time. Delta means change. So, for example, let's look at this one here. It says f of 1 equals 8 and f of 2 equals 20. And so this means at t equals 1 second, an object is located at a coordinate of 8. Okay, so let's just pretend for a second that I'm traveling on a horizontal axis again. So here's 0, let's say 8 is like right about here. So after 1 second has gone by, the object is located right there. But after 2 more seconds, matter of fact, let me put the time up here so I don't forget. And at t equals 2, now the object's located at 20. Okay? Now this question is asking us to find delta S. What is delta S? Well, delta S is equal to f of T2 minus f of T1. Now T2 means my second time. T1 means my first time. My second time was 2 seconds. My first time was 1 second. And from the data here, f of 1 equals 8 and f of 2 equals 20. So f of 2 minus f of 1 is 20 minus 8, which is 12. And what this basically indicates is how far apart those two spots are located. So from 8 to 20 is a total of 12 spaces apart. But it also indicates the direction that we traveled. Okay, and we'll talk about that on the next slide. But that's what delta S is. Now, one more thing to share with you. I want to talk about distance now. There's a little bit of a difference between distance and delta S. Now, it's kind of tempting to say that delta S represents the distance between these points, and it kind of does. But the distance is better represented by the absolute value of delta S, because here's the thing. Delta S can be negative sometimes, okay? And when delta S is negative, that means something. That means something about the direction that it's traveling. So the fact, for instance, that this was a positive number indicates that I went from 8 to 20. So in other words, the position increased. So I ended up with a positive delta S. A negative delta S would mean that my position decreased, okay? But distance doesn't really care about increase or decrease. It just cares about the number itself. So the distance of this object here is the absolute value of 12, which is 12. But remember, it could be, delta S can be positive or negative, whereas distance is always positive. When we talk about distance, it's always in terms of positives. So let's try to bring some of this a little bit more clarification here. Now, in the class, we're going to be dealing with objects traveling on one of two different axes, okay? Vertical axes and horizontal axes. Of course, you could have diagonal axes too, but in this class, we're just going to focus on horizontal and vertical, okay? Now, S represents the position, right? And delta S, let me write that out actually. This represents position, and this represents, these two represent change in position, right? Now, if you're traveling on a vertical axis, then what a positive S value means is it means that your object is located above 0. So for instance, if I told you that my S value was 5, let's say 0 is right here, well, that means that I would be up here somewhere. Okay? A negative S would mean that you're located below 0. So S represents your position. So if you're on a vertical axis, a positive S means that you're above 0. A negative S means you're below 0. Okay? Now, what about a positive delta S and a negative delta S? Well, remember, delta S represents your change in position. So if you get a positive delta S, what that means is that your object moved up. If you have a positive change in position, that means your object went from a lower position to a higher position. If you have a negative delta S, that would mean that your object moved down. Okay? Now let's say you're traveling on a horizontal axis. Well, in that case, a positive S would mean that you're located to the right of 0, because on a horizontal axis, the numbers that are positive are to the right of 0, correct? So this would mean that you are located, your object is located to the right of 0. A negative position would mean that you're located to the left of 0. A positive delta S would mean that your position has changed in a positive direction, which means on a horizontal axis that you would have moved to the right. And a negative delta S would indicate that you moved in a leftward direction. So that's how we will interpret position and change in position on vertical and horizontal axes. So let's go ahead and do our first example here. A particle is moving along a horizontal axis according to the position function f of t equals 10 minus t squared, where t is measured in seconds and f is measured in centimeters. So find and interpret f of 2. Well, I'm sure you guys wouldn't have trouble finding f of 2 because you know that means just plug it in to the function. So 10 minus 2 squared, that's 10 minus 4, which is 6. So f of 2 equals 6. But we want to interpret it. And so what this means is that at t equals 2, now we've got to get our units in here. What kind of units are we using for time? We're using seconds. So at t equals 2 seconds, the object is located. Now I end up with a positive 6 for my position. So that means it's located 6 units, since we're on a horizontal axis, 6 units to the right of 0, or 6 centimeters, I should say. It's to the right because it's a positive 6. All right, next one. Find the object's position at t equals 4 seconds. Now this is just another way of asking the same question that I asked in number 1. This is asking what's the object's position at 2 seconds. So if I ask you to find the object's position at 4 seconds, what that really means is they want you to find f of 4. So plug 4 in so you can find the answer, which would represent the position. So that's going to be 10 minus 4 squared, which is negative 6. What this means then is that at t equals 4 seconds, the object's position is located 6 units, or 6, I keep saying units, but it's centimeters, 6 centimeters to the left of 0, because it's a negative 6. Okay. Now they want me to find and interpret f of 4 minus f of 2. All right. Well, f of 4 represents the object's position at t equals 4 seconds. Now, we already got that. It was negative 6. That was the answer to number 2. This represents the object's position at t equals 2 seconds. And at 2 seconds, we had the position of 6. Now, if we subtract those, I end up with a negative 12. And what that tells me is how much the object's position has changed and in what direction it has changed. So from t equals 2 to t equals 4, the object's position changed by negative 12. Now, you could say the object's position changed by negative 12. That would be fine. But I'm going to say it a little bit differently. I'm going to say the object moved 12 spaces which way? Or actually, instead of saying spaces, let's say centimeters, because we have our units. 12 centimeters to the left. Why left? Because it's negative. So from t equals 2 to t equals 4, the object moved 12 centimeters to the left. Now, what distance did that object travel on that same time interval from t equals 2 to t equals 4? Well, as we said on the last page, distance is equal to the absolute value of delta s, the change in position. Now, we just figured out what the change in position was in number 3. The change in position was negative 12, and the absolute value of that is 12. So the distance that the object traveled is 12 centimeters. Delta s is negative 12. So as you guys see, there is a little bit of a difference between delta s and distance. Delta s tells you how far and in what direction, whereas distance just tells you how far. Okay? So we'll let you guys go ahead and try one of these. Go ahead and pause the video here and try this problem out. But before you do, I need to tell you what kind of axis to use. Now, in my example, I used a horizontal axis, so we were talking about left and right. But let's have you guys say that this object's position is on a vertical axis, going up and down. Okay? So go ahead and pause the video here and try out these problems in that situation. When you unpause it, you'll see the solution. Okay, so the answer number 1 is up here, and then I realized I was running out of space, so the rest of them are down there in red. But for number 1, f of 1 is -8, and what that means is that the object is located 8 feet below, I put above, but 8 feet below 0 at t equals 1 minute. For the other one, says find the object's position at t equals 6, so you're going to plug in 6 into your function, you get 2. That means the object is located 2 feet above the x-axis, above 0 at t equals 6 seconds, because it's a positive 2. So this one is below 0 because it's -8. This one is above 0 because it's positive 2. Okay. Number 3, f of 6 minus f of 1. That would be negative. This is completely wrong. Let me fix that. F of 6 was 2, and f of 1 was -8. And so that actually comes out to be 10. And so what that means is that the object moved 10 spaces up on the time interval from t equals 1 to t equals 6. All right. And then the last one, distance, is just the absolute value of what we found in number 3. Number 3 is what's called the delta S. It tells you the direction the object traveled. It moved up 10 spaces. Distance doesn't care about direction, so we just take the absolute value of that number. But the absolute value of 10 is still just 10, so we have 10 feet as our final answer there, number 4. Okay? Let's move along. All right, so ponder this question here for a second. Suppose that an object is traveling along a vertical axis, and at t equals 3 seconds, the object is located at coordinate 5, and at t equals 8 seconds, it's located at coordinate 20. So we're on a vertical axis, and at t equals 3 seconds, the object is located at 5, so we'll say that's 5, and that's for t equals 3. And then at 8 seconds, it's located at 20. Sorry, t equals 8. We are located now at 20. So now what direction is the object moving? Well, you could tell that it's moving up, right? You could tell it's moving up because from the 3rd second to the 8th second, we went from 5 to 20. So it went in an upward direction. Now, how fast is it moving? How fast is it moving? Well, you guys know that speed is distance over time. So what distance did it travel? It traveled a total distance of 15. And how long did it take to do that? Well, it started off at the 3rd second and it ended at the 8th second. So from 3 to 8 is 5. And so that would mean that it's moving 5 units per second, or whatever you want to say. Okay, so that would be the speed. Speed is distance over time. So that brings us to part 2, where we're going to talk about average velocity. So what is average velocity? Average velocity, I'll abbreviate it like that, is going to be your change in position in other words, how far your object moved and in what direction, divided by the amount of time that went by. So average velocity is your change in position over your change in time. Okay? Now, how do we find change in position? Well, that was delta S, and the change in time would be delta t. Delta S can be found by taking your position at the second time and subtracting from that your position at the first time. Delta T can just be found by subtracting your two time values. Now that formula should look a little bit familiar. That's basically our slope formula, right? Say average velocity is the average rate of change in other words, slope of your position. Velocity is a lot like speed, right? On the last slide we said that speed was distance over time, okay? And so average velocity is a lot like speed, but there is a little bit of a difference. But before we get that, let's talk about the units of velocity real quick. So we'll call that 1. So since we're dealing with position in the numerator and time in the denominator, the units of velocity will always be your position units on the top divided by your time units on the bottom. So, for example, you could have something like feet per second, right? Or you could have miles per hour, right? So velocity is always going to be your position units over your time units, okay? So let's talk about axes of motion and interpreting results once again here, because that's going to mean something to us. If you're moving along a vertical axis, a positive velocity would indicate that your object is moving up. Okay? A negative velocity would indicate that your object is moving down. Now you might notice that's a lot like the delta S, right? Because remember, delta S told us we moved up or we moved down. Well, this one says moving up and moving down. Why are they so similar? Well, you don't have to write this, but delta S tells you how much it moved up, but velocity is delta S divided by delta T. So this just tells you how much you moved up over a certain amount of time. Okay, so it tells you how fast you're moving up. So it tells you your speed at which you're moving up, and it also tells you your speed at which you're moving downward. If you're talking about a horizontal axis, then a positive velocity would tell you the speed at which you're moving to the right. And a negative velocity would tell you the speed at which you're moving to the left. Okay. So let's talk about speed versus velocity, because there is a subtle little difference. You don't need to write this, but as you guys might remember that distance is the absolute value of your change in position, right? Change in position tells you not only how much, but also what direction. Well, that's similar to the relationship between speed and velocity. Speed is the absolute value of velocity. Velocity tells you, as we saw from the last slide here, it tells you what direction you're going also, right? Speed doesn't care about direction. Speed just tells you how fast you're going. It doesn't tell us what direction. So that is an important difference to pay attention to. It's a subtle one, but speed and velocity are almost the same, but they are not quite the same. Speed is the absolute value of velocity. Velocity is a number that tells you how fast and what direction. Speed, since it's the absolute value, doesn't care about direction and only tells you how fast. All right, let's go ahead and take a look at example 2. A billiard ball is dropped from a height of 100 feet, and the ball's height, s, at time t, is given by this position function. S equals negative 16t squared plus 100. All right, so find the object's height at 1 second. All right, so that means we're going to plug 1 in for our time, and the output will be the height of the object at that point in time. So S is equal to negative 16 times 1 squared plus 100. And that's going to give me 84. Now 84 what though? Feet. So at t equals 1 second, my object has a height of 84. So it started off at a height of 100 feet, and then it's dropped, and after 1 second's gone by, now it's at 84 feet. Part B, find the object's height at 2 seconds. So we get to repeat ourselves now, just with a different number. All right, 2 squared is 4, and 4 times negative 16 is negative 64. Negative 64 plus 100 is 36 feet. So now we have this ball, we let it go at 100 feet. After 1 second, it dropped down to a height of 84. Now after 2 seconds, it's now at a height of 36. Now, part C is asking us, what is this object's average velocity on the time interval from 1 to 2? All right, well, average velocity is the change in position over the change in time. Now, the change in position is on the interval from 1 to 2. Basically, it's the second position was 36, so that's where it's located at t equals 2 seconds. And its first position was at 84. Now, by first, I don't mean where it started. It started at 100. But we're looking at this interval here. So at t equals 1, it starts off at a height of 84 at t equals 1. And then at t equals 2, now it's at a height of 36. So we have t2 minus t1. So what we have is s2 minus s1 over t2 minus t1. And it's basically just the average rate of change of position or the slope of your position over time. So let's go ahead and calculate this out. What is 36 take away 84? I think that would be more, it's going to be 848 over 1, and it's negative. So it's negative 48. Now we want to include our units. The top, those are positions. Those are feet values. The bottom, those are time values, which we've seen in the problem are seconds. So what this means is that the object's velocity is negative 48 feet per second. So let's interpret that. That means that the object is moving downward. Why down? Because it's negative. It's moving down at a rate of 48 feet per second. That's what that means. Okay? Now the problem is asking us to find the average speed. Well, as you guys know, the average speed is the absolute value of the velocity. Now, we just found the velocity in part C. The velocity was negative 48, so if I take the absolute value of that, I just get 48 feet per second. So this doesn't tell us what direction, this just tells us how fast. Okay? So we did 4 things. We found the object's position at one point in time. We found the object's position at another point in time. And from that, we can tell what the velocity is. We can tell what direction it's moving in and how fast it's moving in that direction. Okay? So let me throw one of these at you guys. And this is going to be student practice 2. So go ahead and pause the video here and see if you guys can answer this question. All right, so here we go. The first thing we got to do is we want to look at the fact that we're looking for the speed. Okay, now speed is velocity, the absolute value of velocity. Velocity can be found by taking your second position and subtracting it from your first position and dividing that by your second time minus your first time. So we need to find out what these S2 and S1, T2 and T1s are. Well, the time interval they give us is 0 to 20. So T1 is 0, that's my starting time. My ending time is 20. So I know what goes in the bottom, 20 minus 1. But now I need to figure out what are my positions. Well, that's what this function is for up here. If you plug in 20 and 0, you can find your positions. So by plugging in 20, I can find out my second position, which is 6,100 feet. And by plugging in 0, I can find my initial position, which is 12,500 feet. So S2 minus S1 is 61 minus 12,500. So we subtract those and subtract these and divide them, and what we end up with is negative 320, but we are taking the absolute value of it because they want the speed. So we end up with a speed of 320 feet per second. Now I think it's important you guys understand we're talking about average speed. Really, if somebody's diving out of an airplane, they go faster and faster and faster. So they have average velocity and average speed, which is your final position minus your starting position over however much time it takes. But really, at any given point in time, your speed is constantly changing. All right, let's take a look at another example. Only instead of giving you guys an equation, this time I'm going to give you a table. So, the table below gives the height of water in a fish tank as a function of time. So basically, it tells you at a certain time what the height of the water is in the tank. So at t equals 5 minutes, for instance, the height of water in the tank at that point in time is 15.5 inches high. All right, it says answer the questions that follow. So we want to find the average rate of change on the interval from 2 to 7. Now those are time values. So we want to go from t equals 2 to t equals 7. Now at 2 minutes, the height is 10, and at 7 minutes, the height is 18.5. So the average rate of change is going to be equal to 18.5 minus 10, the second height minus the first height. You could write it like this at first if you want to, over the second time minus the first time. Second time is 7, the first time is 2. Okay, and what that leaves me with is 8.5 over 5. Sorry, 8.5. I put 8.4. Fix that real quick. 8.5 over 5, which we can get a calculator out and just change that into just a solid decimal instead of fraction and a decimal. And I get about 1.7. Now, I want to include the units, though, on this, right? The top, those are numbers from height. So those are inches. The bottom are 7 and 2. Those numbers come from the top row, which is minutes. So what we have here is 1.7 inches per minute. Now you'll notice that since it's a positive value, that means that you can assume that the height of the water is increasing by 1.7 inches per minute. Now you'll notice that I changed my wording a little bit as I wrote it. I put the height of the water is increasing on average by 1.7 inches per minute. Okay, so, and once again, that's bringing us back to this point that there's a difference between average rate of change and instantaneous rate of change. All right, so I'm gonna, before I do number 2, what I want to do is I want to review something with you guys. What's the difference between average rate of change and instantaneous rate of change? Well, average rate of change is the slope of a secant line. Instantaneous rate of change is the slope of a tangent line. Okay? So what we can do, though, when you're dealing with tables, and by the way, this is a really common AP question. Very common on the FRQs. What you can do is, when you have a table, it's impossible to get an instantaneous rate of change unless they give you a derivative value somewhere. But in this case, they don't. But you guys agree that if I were to pick 2 points, I can find the I can find an instantaneous rate. I'm sorry, I can find an average rate of change. All I need to do is take 2 points and find their slope, right, between those 2 points. But that's an average rate of change. But if you pick 2 points that are really, really close together, especially to that point where you're trying to find the instantaneous rate of change, and you connect those dots, that line almost has the same exact slope as the tangent line. So the closer the points you pick to the tangent line, the more accurate that average rate of change will actually match your instantaneous rate of change. So we can't actually find an instantaneous rate of change when you have a table like this. But what you can do is you can estimate the instantaneous rate of change at a specific time by picking 2 points that are closest to that value in the table. So they want us to use the given values to estimate the instantaneous rate of change at t equals 6. So I want to find the 2 time values in this table up here that are closest to 6, and that would be 5 and 7. So if I can find the average rate of change from 5 to 7, then that average rate of change will be the closest slope I can get to what the instantaneous rate of change is, which is somewhere in the middle here at 6. So the instantaneous rate of change at t equals 6 is approximately equal to the average rate of change on the interval from 5 to 7, because those are the 2 time values that are closest to 6. And that can be calculated by doing height 2 minus height 1 over time 2 minus time 1. And remember, this is in inches per minute. So even though we don't really know how fast the water is increasing at t equals 6 seconds exactly, we can estimate that it's increasing at a speed pretty close of 1.5 inches per minute, because those are the 2 time values that are closest. 5 and 7 are 2 time values that are closest to the actual value we want. So that's a very common AP question. All right. So that being said, let's have you guys try a problem like that. Go ahead and pause the video and try both of these, and when you unpause it, you'll see the solution. All right, so the answer to A is at the top. We're finding the average rate of change on the interval from 1 to 10. So you do your time 2 minus time 1 over your height 2 minus height 1. So the height at 10 is 4 and the height at 1 is 1.8. Calculating our slope, we end up with 0.24 and it just kind of keeps going. And that's in feet per minute. The top numbers come from the bottom row, which is in feet. The bottom numbers come from the top row here, which is in minutes, so it's feet per minute. Part B, estimate the instantaneous rate of change at t equals 2. The instantaneous rate of change at t equals 2 is approximately equal to the average rate of change on the interval from 1 to 3, because 1 and 3 are the numbers closest to t equals 2. And so if you calculate the slope, or the average rate of change on that interval, you would get about 0.45, and once again, that's inches per minute. Okay? Moving on. Let's talk about instantaneous velocity now, a little bit more in detail. Now, on the last page, I was talking once again about how you have the average rate of change versus the instantaneous rate of change, right? Well, actually, let me do it this way instead. So this would be a tangent line, and its slope gives me the instantaneous rate of change. This is what we call a secant line, this one here, and that gives me, the slope of that gives me the average rate of change, right? Well, and we also talked about how the closer the points of your secant line are to the point of your tangent line, the closer those are together, the better the average rate of change matches the instantaneous rate of change. So if you take your average rate of change and you find the limit of that as your second point gets closer and closer to your first point, you end up with the instantaneous rate of change. All right, so in other words, if you take your average rate of change, which you guys know is f of t2 minus f of t1 over t2 minus t1, and you find the limit of that as your t2 approaches t1, as your second time gets closer and closer to your first time, you end up with the instantaneous rate of change at that time. Okay, so once again, I mean, all I'm really trying to point out to you guys on this slide is the fact that instantaneous velocity is the derivative of f. Now, what does f represent once again? It represents your position. So it's the derivative of your position function. So that's the big aha I want you guys to walk away from with this slide, is that if your position function is f, whenever you do f of t2 minus f of t1 over t2 minus t1, that gives you the average rate of change. But if you find the limit of that as those two times get closer and closer together to becoming a single point, you end up with an instantaneous rate of change. And the instantaneous rate of change of position is velocity. Okay? And so that's the idea there. Now, whenever you're doing instantaneous rate of change, what's not so obvious is what the units will be. But the units for instantaneous rate of change, or in this case, I guess we're saying instantaneous velocity, will be the same thing as average rate of change. So it's always going to be a position unit, like feet, inches, miles, centimeters, whatever, over a time unit, like seconds, minutes, hours, whatnot. So your units for instantaneous rate of change or instantaneous velocity will be position units over time units. Okay? So let's go ahead and take a look at one more final example here. All right, a diver jumps off of a diving board. The diver's position is given by this function, where s represents the height above the water in feet, and t represents time in seconds. So the first thing here says find and evaluate f of 1. f of 1 is what we get when we plug 1 directly into the equation that they gave us. Now that's a position function. So when you plug a time in there, it gives you a position. And what we end up with there is 32. And we said 32 what? That's going to be 32 feet. And so what this means is at t equals 1 second, the person's height is 32 feet. Okay? Now the next question says, find and evaluate f prime of 1. Well, if f equals this, then f prime is what we need to find next. The derivative of this is going to be negative 32t plus 16, and then 32 goes away, right? But what does this mean? Well, we know this one here represents position, so let's write that down. But what does the derivative of position represent? Well, we just said on the last slide, the derivative of position is instantaneous velocity. Let me put instantaneous, because we have talked about two kinds of velocity, instantaneous versus average. And the derivative is an instantaneous velocity. In other words, this is a function that will tell you what the velocity of this diver is at any given point in time. So f prime of 1 is going to be negative 32 times 1 plus 16, which is negative 16. Now we want to get our units right. What did I say the units would be? It would be position over time. So what units are we using for the diver's position? The units for the diver's position are feet. And what units are we using for time? Seconds. So what this means is that the diver is going in a downward direction, because it's negative, at a speed of 16 feet per second. So the diver is being pulled down to the earth at a rate of negative 16 feet per second at t equals 1. So I think we should write that down there. So let's do that. At t equals 1 second, the diver is moving down. Why down? Because it's a negative 16. At 16 feet per second. Now, another way you could say this is you could say that at t equals 1 second, the diver's velocity is negative 16 feet per second. And I think you should write both. So let's write the other one. Now notice how whenever I say it's its velocity, I just say negative 16 feet per second. But if you put the direction in there, moving down, that is your negative. So you don't want to put the negative here, because if you do, that's like a double negative. So the moving down is your negative when you describe it like this. And if you describe it as just a velocity, you'll write it like this. And I would encourage you guys to write it both ways. You can see it presented to you in both ways, and you don't want to mix those two ways up. So you want to have them kind of written out and be distinctive from each other. Now there's two other questions on here, but they're not quite as important as the first two. So I want to stop there for a second. I want you guys to practice the basic idea here. So I want you guys to do number 1 and 2 on this problem. Go ahead and pause the video here and give those ones a try. Okay, so I have the number answers written here in purple. The answer to number number 1 is 2 meters, and the answer to number 2 is 0.2 meters per second. But we want to interpret these as well. Now, when you do an interpretation, guys, I've mentioned this a few times in our FRQ videos, is we need context. That means what's the story about? This is about a baseball's height. We need input units. So t is the input variable, so at a height of t equals 0 seconds, and then we need output units. And so that would be is 2 meters. So the baseball's height is at t equals 0 seconds is 2 meters. Now the interpretation for number 2, though, that's a derivative. And what's the derivative of position? The derivative of position is velocity. So this is a velocity. So the 1 represents a time, and the output that we get represents the velocity. So you could say that the baseball's velocity is 0.2 meters per second, and I forgot something, at t equals 1 second. Remember, you need the input units and the output units. Or you could say the baseball is going up at a speed of 0.2 meters per second at t equals 1 second. So I left off my input units on both of those. But anytime you do an interpretation, you should have all three. You should have the context, the output unit, and the input unit. Context, input, output. Now, the difference between these two different ways of writing it is this one just says what direction the ball is going. So you could say the baseball is going up at a speed of 0.2 meters per second. This one is just saying the velocity is 0.2. All right? All right, now I want to go to one more thing before we call it a day. And it's a question that's really not as important, but it'll help you with a homework question. It'll make you think a little bit deeper about all the stuff that we've learned. All right, so what I'm going to do is I'm going to ask you how long it takes the diver to hit the water. And then I'm going to ask you what is the diver's velocity at the moment they reach the water. Now, usually when this question is asked, this is all that they're going to ask you. So they're going to say, what is the diver's velocity at the moment he or she reaches the water? So the first thing that we need to do is we need to know when they reach the water. And that's why I put part C up here. So the first thing we want to do is find out how long it takes to hit the water. And once you know what that time value is of when it hit the water, you can just plug that right into your derivative, and it will tell you what the diver's speed is or his velocity at that point. Okay? So how long does it take for the diver to hit the water? For that, you're going to take your position function. We don't know what t is, so I'm going to leave the t there, but we do know the diver's position when he hits the water. We know what his position would be. This represents height. So once he hits the water, what's his height? It would be 0. Okay? Now, from here on out, you're going to use the quadratic formula. Sometimes you can factor these, but I wouldn't count on it. Quadratic formula is going to come in handy every once in a while. So I'll go ahead and set that up. I'm going to pause my video, and when I unpause it, you guys will see the worked out final solution there. But you do want to know how to do the quadratic formula. So once you plug in your A, B, and C into your quadratic formula and simplify it, that'll tell you the two t values at which you have a position of 0. One of them is -1, and the other one is 2. If you simplify this, you get 2 answers because you add and subtract, right? Now, for the -1, we're going to throw that away. There's no such thing as a negative time. So the answer is that the diver hits the water at 2 seconds. Now the question is, what's the diver's velocity at the moment he or she hits the water? Well, now we know when he hits the water, but now we want to know the velocity. The velocity would be f prime of 2. All right? So we've already said that the derivative was -32t plus 16, right? So f prime of 2 would be -32 times 2 plus 16. And that's going to be negative, I'm inclined to do mental math, but I think I'll get it wrong. So I'm just going to go ahead and do a calculator real quick here. I think it's -48, but yes, -48. But we want to interpret it now, right? That's -48 what? Feet per second. And I'm not going to write out the interpretation. I'll just write the answer there. But that's the diver's velocity, is -48 feet per second. So at the point in time when the diver hits the water, which is at 2 seconds after they jumped off the diving board, the diver has now reached a speed of -48 feet per second. All right. So I'm going to let you guys try one like that now on yours. Now for you, I'm just asking, what is the baseball's final speed? So, but that's telling you to do something. You have to find when it lands on the ground. Okay, so once again, you're going to plug in 0 for your position because that's when the baseball will be on the ground. You're going to solve for t using your quadratic formula, and that will tell you when the baseball lands on the ground. And after that, you can find the object's velocity and speed. So remember, you're going to find its velocity first, but after you find the velocity, since your problem is asking for speed, you need to take the absolute value of your answer to get the final result. So go ahead and pause the video, give it a try, see how you're doing. When you unpause it, you'll see the solution. All right, so first of all, if we want to find the ball's final speed when it hits the ground, we have to find when it hits the ground. So we set our position function equal to 0 to indicate that it lands on the ground. Using the quadratic formula to find the values of t for which that will happen, you get 2 answers, but once again, you throw away the negative one. So it lands on the ground after 2.2 seconds. So now if you want to find the speed at 2.2 seconds, the point in time whenever it touches the ground, we're going to find the velocity at 2.2 seconds and take the absolute value of it. The velocity is the derivative of the position function, which we already know to be this. So if I plug in 2.2 into my velocity function, I get negative 11.56. But since we want speed, we take the absolute value and end up with a positive output of 11.56 meters per second. So the ball lands on the ground at 2.2 seconds, and when it does so, it's going at a speed of 11.56 meters per second. And that's the end of it. So we'll go ahead and stop there with lesson 4.7, and we'll see you guys next time for 4.8.